Hi, everyone, and welcome to another episode of Pathfinder, a podcast by Payload, the leading digital media company in the space industry. My guest today is Livingston Holder, the co-founder and CTO of Radian Aerospace, the developer and operator of a single-stage-to-orbit spaceplane that's looking to do their very first flight test this year. We talk Livingston's life before Radian as a U.S. Air Force astronaut, Radian's origin story, and a lot more. But first, a word from our sponsors. This year, the Italian trade agency showed up in full force at the National Space Symposium in Colorado Springs. They exhibited 12 groundbreaking companies showcasing their technologies all under one roof. From aerospace giants to pioneering startups, the Italian pavilion this year represented a diverse spectrum of expertise and creativity, combining tradition and innovation. Moreover, this year saw the largest Italian delegation the conference has ever seen in attendance. For more information about what the ITA is doing for the global space community, be sure to check out their website at www.itahouston.com. Livingston, thanks so much for joining us today.
Glad to be with you.
I see you got the scientists' desk set up. You got TV screens. You got notebooks all over.
I have more monitors than one should actually ever have, and I'll just leave it at that. People come up and say, "Why do you need so many screens?" But I use them.
In my previous life, I worked at a bank on Wall Street, and I had, I think the most screens I had was 6. So maybe, I don't know if you beat me on that, but
actually I have 6, but one is not active because it just failed. It just gave up and said, "I quit." So it hasn't been replaced yet. It may not be. So I may limit it to. I forgot the screens on my desktop here. So.
All right, so you beat me on this. You beat me on the screen game. I'll give it to you. So Livingston, before we jump into Radian, I want to talk about your career, because you've had a very, very interesting one. You've done a lot, you've done a lot of things, and I want to start from the very beginning. How did you get interested in space? How did you get interested in the space program? What made you want to become an astronaut? Let's start from the very beginning.
When I was little, that's when. In grade school, that's when the Gemini and Apollo programs were going on. And so I would have a radio in my bedroom tuned to the news. Yeah, that's a good look for a kid. You got a radio, and what are you listening to? The news, right? And I would always be following the NASA missions, no matter what they were. And if it wasn't on the TV, it'd be on the radio. So I was always watching that. And I figured, hey, that would be a great thing to do when I grow up. And I never lost that love of wanting to be an astronaut, the love of doing technology work in space and airplanes. And so it just continued. My big problem was my eyesight was poor. And I couldn't pass any of the thresholds, like at the Air Force Academy, to become a pilot. They said, they said you cannot fly with these eyes. And now cadets are having laser surgery to correct their vision, so that they may not enter the academy with pilot qualivision, but they'll leave the academy with pilot qualivision. And so it was frustrating not to be able to do that. So I took another track, which was technology oriented, to say, well, maybe they'll need me in the back of the shuttle to work on the payload. So that's where I put my energy. But it's been a lifelong dream. It really has.
So you couldn't qualify to be a pilot, but you qualified to be an astronaut. I think that's a great plan B.
Well, and see, the thing is, that's something the shuttle allows. The space shuttle was the first time that we had people who weren't pilots flying as astronauts. So that was a huge opening of the aperture of who could become an astronaut. Was the shuttle program, and so I was perfectly timed for that.
What was it like to go through the program?
Well, we did something different than what NASA did, because I applied to the Air Force program, and the DoD program was separate from NASA. Our payloads were almost all classified, and therefore Not everyone at in the NASA astronaut corps could be made aware of them, and so we trained kind of separately. Like we would take simulator time late at night while the NASA guys would be during the day. So it was very, very interesting because we ran this parallel track for years, and then at the end we would integrate the payload, the shuttle, the payload specialists. We were called manned space flight engineers, or MSEs, and the NASA crew, almost at the very end of the uh, cycle for getting something to orbit. So it was really kind of weird because a lot of the NASA folks were like, "Who is this guy?" You know, the ones that were classified and briefed on what we're doing, they knew what we were up to, but that was a very small group of them with respect to the larger set. So it was very interesting. Very interesting.
Were there any obvious cultural differences between the programs and the people?
Yes, we in the Air Force, or the DoD side, because we had one naval officer in our group, we were very focused on the payloads, the mission. The NASA astronauts they had to be flexible because they have to fly with any payload on almost any given shuttle. And so the payload training for them was a smaller portion of the work than it was for us. The payload was our reason for being, and the only reason that we win is because we're flying a mission payload. And NASA had built up a culture unto itself for astronauts, and we on the DoD side really weren't part of that. The only time you had DoD guys become part of that culture is when you were assigned to NASA as an astronaut from one of the military services, but then you came under NASA's banner, their training program, their culture, etc. We were never assigned or detailed to NASA. We always stayed on the DoD side. So that created some interesting uh, cultural uh, differences.
So, what was life after the program?
Um, it was tough at first because you know my mission was supposed to fly on Challenger, not the mission that was lost, but it was going to come some iterations afterwards, and it required a high energy upper stage. So we had a LOX hydrogen Centaur upper stage in the payload bay to get our payload to the proper orbit. And um, after the accident, um, NASA killed that program and it said, okay, we're not going to put liquid hydrogen, liquid oxygen in the payload bay um, for these missions. And that then took my vehicle out of the shuttle. And when my vehicle transitioned from the shuttle, I started working on transitioning it to an expendable launch vehicle. So when it left the shuttle, so did I, and so it was really hard to um, to lose the opportunity for space flight, which is something I'd always wanted to do. I mean, from the time I was very young, even today. So it was kind of tough to lose that. But what I was able to do is turn my energy into those things that facilitated space flight, that facilitated new development, and so I was, uh, I still got to do a lot of really fun things. I just was missing that one element of getting the flight in.
So, I something tells me that there will be opportunities for you, Livingston, to go to
Working on it,
space.
working on it.
So tell me. Okay, let's talk about Radian for a second. So, how did you go from transitioning to working at established firms like the Primes, right?
Yeah.
To now co-founding Radian. Tell me a little bit
It,
about that journey.
it was a big challenge. The first one was when I left the Air Force because I went to the academy. I served in launching vehicles. I served in developing payloads. And again, it's a very large, well-structured organization. And when you have something that large and structured, you you find a place to slot in. Here are the rules. This is what you do. This is what your training looks like, et cetera. So after I left the Air Force, I went to work for Boeing. Boeing is a big, large enterprise that is well structured. Matter of fact, I saw a lot of things in the Boeing structure that reminded me of how the Air Force did business. And I think when you have very, very large organizations, you need a lot of structure. So that transition, albeit difficult, was not, I'll say, as difficult as when I left Boeing and went to a small company. I went to Andrews Space, and that was kind of the culture shock, because now you're not in a organization of thousands of people. You're in an organization of tens of people, and you do a lot more for yourself. Everybody has multiple jobs that they have to do, because you don't have a big enterprise to do all that work. That wasn't as bad as I thought it was going to be, because at Boeing, I had historically worked on relatively small teams. We developed a team to go try this out or try that out. And I kept those teams relatively tight so that information flow was fast and our ability to maneuver and do things was fast. Even though we were part of a much, much larger enterprise, the teams I managed typically were small until we got to space station. Then they kind of blossomed, and the X-33 program was kind of big too. So that transition was a little more challenging, but some of the folks that worked there had large enterprise experience. So we kind of we kind of got the flow, if you will. It says this part of the large enterprise experience wasn't really necessary. You had to go through all these check cases before you could get permission to do something. Well, the chain is two people, so it made it faster. So it was an interesting transition, a lot of flexibility, lots of freedom, but it was just a really different way of thinking about things. But it was kind of easy for me in that I always felt the smaller teams were more agile and could get more stuff done, and as long as they had the resources to do it. So I suppose it worked out pretty well for me.
Well, you're building a very interesting company now, right, Radian? So tell us, high level, what is it that you're building? I know the folks that have been listening or watching on video can see that loop of the plane,
Oh yeah, that's
over and
the
over.
website in the background. Yeah.
There it is. So no, tell us a little bit. So what is it that you're building?
Um, in the most basic of terms, it's a space plane. It's fully reusable, and it will fly horizontally to space to get to orbit, and then come back down horizontally to land. And the landing part, people kind of get because they've seen the shuttle come home that way. There are other reentry vehicles that come home that way. But the takeoff part is what's really unique here, in that we take off horizontally like an airplane, and we actually use our wings to fly to orbit. So the idea is to make the system more operable than a traditionally vertically launched vehicle. You want to make sure that it's robust enough so that one tail number can fly many, many missions. You want to make sure that it is operationally efficient enough that you can turn it around quickly. You don't have to rebuild your rocket or build, like expendables, you have to build the whole rocket each time you want to fly. With some of the reusables, you still have to build portions of it that you throw away. For us, we really want to not throw away anything. And so I sometimes use the term gas and go. You land, you put propellants in it, your new payload and your new crew, and you fly. So it's really reusable, uh, single stage to orbit space plane, and it's got extraordinary flexibility. You can deploy satellites with it. That's kind of a starting point for a lot of missions. You can do servicing missions because you have a crew, and so if there's something up there that needs to be serviced, you can do that. You can do return missions. So let's say you're a company and you're building something that needs to be built in space because you want the zero gravity capability. Now you got to try and get it home. If you try and get it home in a capsule and a parachute, it kind of limits the amount of mass, the space that you can use. With us, you can fill up our payload bay, and we can come home and land, and you can take your object off as if you were transporting it, I'll say via airplane. So it gives you a lot of flexibility to bring down more mass of those things that are either manufactured in space, they've gone dormant, you want to bring them home. So it gives you just an enormous amount of flexibility for everything from scientific research to transitioning to systems that, because you can't do that today, that will be enabled by Radian's existence tomorrow. And those are the ones that are harder to predict. But those are the ones I think are going to be most exciting, because the common thing people talk about is the iPhone. You wouldn't have Uber if you didn't have an iPhone. And so there may be something out there that you wouldn't have if you didn't have a Radian, because you enable capability that is not enabled today. So I'm looking forward to it. It's exciting.
So no, very exciting. So one thing that we did look over was the nature of how the Radian spaceplane takes off, because it's not, just to be clear, right? We're not taking off on our wheels. So maybe talk a little bit.
Right.
Maybe talk about that for a second.
We have a sled, and the sled does two things. So if you picture the space shuttle. Now the space shuttle had a big orange external tank. That tank held all the propellants for the main engines, and so it stayed with the shuttle until they got to orbit. It also had two solid rocket motors, two solid rocket boosters, and those fired for about 2 minutes and gave you enough impulse. They weren't very efficient, but they got you going. So the combination of that solid rocket booster and the external tank are embodied in our sled. The sled has 3 engines of its own, and so it provides acceleration for the system. And that helps you get to the point where you've got enough velocity to take off. But it also has tanks inside it that feed the 5 engines on the main vehicle. And what that does is it allows you to take off with full tanks. And if you think about it, sometimes rockets rumble on the ground for a little bit, and then they finally take off. Well, the propellant in the tanks goes down, which means that they're flying with a portion of the tank empty that they never use. So the weight for that part of the tank, that dry mass, is a penalty that they have to carry throughout the entire flight. We're trying to minimize that. We need to take every advantage we can, and a sled on rails seems to be the best way to do that.
So let me make sure I understand this. So it's a sled that has its own engine and propulsion capability, I should say. And along with propulsion capability, there is an additional element of fueling the vehicle while the sled is propelling the vehicle at the same time.
Right.
I understand.
Yeah. So that's the external tank, if you will. Part of the analogy is that the external tank fed the main engines on the shuttle. Our tank inside the sled does the same thing.
I understand. Who came up with this?
It's been, by the way, the idea has been around for a while. You can go all the way back to studies performed by Boeing under the RASV program, in which they studied a variety of ways to do this, and actually put forth proposals to the Department of Defense to build something like this. But you can go back farther in time and see others like Sanger, who developed horizontal takeoff, horizontal landing concepts. So it's been around, but it hasn't been practical yet. So the key is, with today's technology, you've got engines that are more efficient, you've got structures that are lighter and stronger, you've got the ability to subcool propellants, so you can get more propellant into a particular tank of a specific volume. So there's been a few things that have happened over the years that make some of those early design concepts more realizable today than they were at the time they were originally thought of.
So I want to take a quick step back. Just talk about single stage to orbit. Maybe let's just do quickly. What is single stage to orbit, and what are the costs and benefits versus traditional vertical launch?
The idea of single stage to orbit is using one vehicle for the entire mission and not throwing anything away. The analogy a lot of people use is a commercial airliner. If you had to rebuild part of your commercial airplane, you would, one, take more time on the ground while you rebuilt those parts. Two, you'd have much longer turnaround, so you couldn't, get the passengers off and the fuel in it to fly frequently. So with this, you don't have to reassemble anything. You could use the term gas and go. The thing you have to do is take out the old payload that you brought down and put the new one in if you're doing a different payload. So the idea behind single stage orbit is to increase the operability of the system, which allows you to increase cadence and standardize interfaces for mechanical, electrical, data, and thermal systems, so that you can fly frequently, and that will bring the cost of operations down, and that flexibility opens up the aperture to new types of missions. So was I answering the question you were
No,
asking?
it did. The other thing I was sort of getting at was this idea of most traditional vertical launch vehicles have vacuum optimized engines, right? As they travel higher up in the atmosphere. How does a single stage to orbit vehicle solve for that?
We actually have a nozzle extension. So usually the first stage of a traditional rocket is optimized for lower atmospheric performance. So the area ratio, the ratio between the throat and the exit of the nozzle, is optimized so that the exhaust goes in the direction you're going. When you get to the upper atmosphere, that's harder because that makes the engine bell much, much bigger. And so, but you have the opportunity to have both a lower stage engine and an upper stage engine, and therefore you can kind of optimize it between your two stages. For us, we have to change our nozzle as we fly. So at the lower portion of the orbit, we have our nozzle extension retracted, and that optimizes for the atmospheric pressure that you start with. And as you get higher and that atmospheric pressure drops, you extend nozzles, and so that gives you a variable area ratio system, so that you are now efficient in both your lower atmosphere as well as your upper atmosphere. By the
Why
way,
don't
this is
you?
not the first time that's been done.
I was just about
Uh,
to ask that.
yeah, the RL10, and it's done for packaging purposes more than anything else. When the upper stage for that system separates, the first thing that happens is the nozzle extends. And so that's done on RL10 is a liquid oxygen, liquid hydrogen engine that's used in upper stages. That's done there. The IUS, that's the inertial upper stage that was built by Boeing years ago. It was a two-stage solid rocket motor system, but the upper stage for it would also have a nozzle that extended. And so this is not the first time it's been done, but it's historically done for packaging purposes. But we're doing well because they couldn't fit the nozzle that they wanted in the space that they had. So for us, we've got the space, and we're going to extend the nozzle at the time when we need it.
I'm going to ask an ignorant question. I'll say, why don't traditional launchers just do nozzle extensions on their first stage? Why do we need two multi-stage vehicles in that case?
I'm going to answer this by talking about why do we need staging. So as the first stage runs out of propellant, it now becomes a drag, both literally and figuratively. You're carrying mass around of a big tank and big engines that you no longer need. And so what we typically do is we drop it. And if you look at the rocket equation, we kind of break the rocket equation into pieces. And the first part gets you to this altitude, this velocity, and with these losses that have taken place, gravity and drag losses. And then you're just carrying this big monster tank around, so you get rid of it. And now what you do is you have a smaller tank, and you optimize the engine for that portion of the flight. So staging is what really causes us to go from a unoptimized lower stage for high altitude flight to an optimized upper stage for high altitude flight. And with us, since we don't stage, we have to try and make sure the engines are as efficient as they can be throughout the entire flight profile. So, if we were a stage system, We probably have engines optimized for lower altitude work and engines optimized for high altitude work. But since we've got to take the engines all the way to orbit, we have to do that optimization as we fly.
So,
I hope that answered the question.
no, that does. So by definition, you've started this company along with Richard, who we'll talk about in a second. But you started this company because the time is right, right? You believe that the time is right. Why has the time not been right up until now? It looks like components. Okay.
Technology. Okay, so let's wind back the clock to the X-33 period. And NASA had the vision of doing a single stage orbit system. But NASA also had constraints on what they wanted it to do, how much mass they wanted it to carry, et cetera. And there was a lot of technologies that were not mature at the time. We are a composite vehicle. And if you were to go back to the X-33 time frame and look at composite technology, we were still kind of learning about composites. So we didn't have as robust an industry. We didn't have as robust a test approach, determining materials allowables, et cetera. So we weren't smart enough to do composites back then. It was very, very much a research and development activity when it came to composites. And so now the composites industry is really matured. You have all composite commercial airplanes. We've had all composites military airplanes flying for years, even ahead of those. So the transition has made those technologies that we rely on more available and significantly better understood. Now, we'll take the composites to different temperature ranges and bending forces, et cetera. So we'll have to test outside the bands of what's been tested for commercial or even military application. But the bottom line is we've got a huge section of knowledge to start with, and we're just expanding that a little bit. So composite technology was probably number one. The other is propulsion technology. I'll use the space shuttle main engines as an example. That was a reusable LOX hydrogen engine, and we determined that it was so difficult to operate that we would pull the engine off the vehicle, take it through an engine shop to get refurbished before putting it back on a vehicle. Again, using the airplane analogy, you really couldn't see somebody taking off your jet engines after you landed, taking them through a shop and fixing your airplane up with a new engine. So engines have become more robust and reusable as a result of our experience all the way from the shuttle era to now. So again, technology has marched on, and we're leveraging that march. Also, back then, you wouldn't see a LOX methane system fly. And now we're realizing that that's a really good propellant combination. It's got high energy. It's not as cold as liquid hydrogen. So we're not asking the composite tanks to go beyond liquid oxygen temperatures. So again, those things just really weren't mature. Stage combustion systems were still pretty immature. Now they're kind of standardized. So technology has marched, and we're taking advantage of where it's marched to. And it hasn't always marched for, our industry alone. Like some of the aircraft work, we didn't think about that a lot for space, in terms of composite materials, but it really has space applications when you apply it. So technology has marched on and given us an advantage.
And I assume you're using methane, liquid oxygen for the engines? Okay. Let's talk a little bit about, we're going to take a couple steps back. Talk a little bit about Richard, how you met Richard Humphrey, your co-founder, and talk a little bit about the origin story. How did you guys come together? What was the spark where you were like, oh, yeah, we're going to work on this?
Are you familiar with the Midland Spaceport?
I'm not.
Okay, so Midland, Texas, had an airport, and they wanted to actually turn it into a spaceport. There was a system flying out of there called X-Corp, and it was a rocket plane. And one of the people associated with that was a fellow named Jeff Feige. Jeff was building the high altitude pressure suits for X-Corp. some of the Midland folks were visiting him on a trip to Southern California, and I was visiting the space shop that he was operating out of, and they invited me to dinner. And um, I was thinking, hey, that's very nice of them. So I enjoyed the dinner and sat at the end of the table, not really involved in what they were involved in. Somewhere in the process, somebody at the other end of the table or far away from me said, can you build an altitude chamber? Well, the altitude chamber is where you test spacesuits, and you can test crews in it. And I've been in altitude chambers in my Air Force career, and I said, if I can do the math, I can probably build one. It wasn't that difficult. And so then I sent that message back, and the message came back down. Says, well, how much will it cost? So the message went back up. Well, I'm not sure. How big do you need it? How many people, et cetera? And I said, well, what do you think you need to do first? And so I went to my hotel room, started sketching this out, and then ended up bidding and then building what's called the Midland Altitude Chamber Complex for Jeff Feige and in the Midland Spaceport. X-Corps went out of business, and Richard Humphrey was an investor or potential investor. You'll have to ask him where he was in that environment. I think he was an investor in X-Corps. And when X-Corps was going out, I think he was left with a desire to still create something to fly people to space. And he and Jeff Feige were out in Midland and chatted about it. And Jeff said, well, if you want to figure out if that's possible, you got to talk to Livingston. And so Richard invited me to dinner in New York, and we had a long evening. And he got really excited, and I said, Richard, this is really hard. This is really, really hard. I've done this work before, and this is hard. But he was really up for the challenge, and we kind of concluded that the time is now. So then we put our heads together. My business partner, Curtis Gifford, who I'd worked with at Holder Aerospace for years and years and years, had the financial, and analytic skills to help us operate a company, and so he joined us as a co-founder, and we spent almost a full year seeing, is this really in the art of the possible? And we worked on a variety of configurations. We brought in some outside experts that they weren't all convinced that we were sane, but they saw the math and said, you're on the edge. This could work. This could work. And so it kind of validated our thinking that it really could work, and we weren't just, redoing our own math and getting the answer that we wanted. But it was a challenge. So that's how I met Richard, and the rest is history.
Where's the company today? Are you guys in testing mode, design mode? What's the where does the development of the plane stand?
Yes, all the above. So we are getting ready to go through design cycle 12, and so we go through structured redesigns of the vehicle so that we can improve like structural efficiency or volumetric efficiency, or so there's some feature that you want to incorporate, and you've done trade studies and analyses that help you understand, does that feature actually add value to the program, or does it just cost a lot of money and doesn't add much? So we go through these structured processes, and we're on AV12 this week. We'll actually codify that. But there's some things that you still don't know. So those things continue in the trade space and the analytical space below the vehicle design level. So that's where. And by the way, there was a whole series ahead of that went up through R4, a whole different numbering system, et cetera. So it went through Radian 4. But then when we changed propellant combinations, we started the air vehicle nomenclature. So we're on AV12. We've done wind tunnel testing at the Air Force Academy to make sure we understand the performance of the system as it flies through the atmosphere. We've done tests at Mach 0.9, 1.2, 2, and Mach 3. I hope I got those right. So we're in that phase of testing. We've built our first composite dome Pathfinder. We have a thing called TT1, Test Tank 1, very cleverly named. And we wind those tanks on a big tool, and we wanted to make sure that we understood how the manufacturing processes would work. So there's a tool and a capability out at University of Washington's Advanced Composite Center. So we've gone out there and we've wound the first two big domes of our tank system that represent kind of the fuselage tank, and that's really to understand the manufacturing aspects of it. What tolerances do you put as you lay this material down using this big robot? How do you cure the material to get the best performance of the material to the specification? And then you do a whole series of things where you torture the material, you punch a hole in it and see how well it'll handle having a hole in it, because you might have a bolt hole. You squeeze it, you freeze it, you heat it, you bend it, you break it. So there's a whole series of structural tests that go on, and then you come up with material allowables. What can I allow this material to do? As long as I operate within this temperature range, within this strain environment, etc., this material will operate repeatedly, because you're not doing anything to it terrible. So we're in that phase as well. We also just finished up a series of thermal protection system tests at Glenn Research Center. Glenn is in Cleveland, Ohio, and they have an excellent materials branch. And unlike other reentry vehicles, we use a combination of hot structures material as well as thermal protection and insulation materials. And the outer portion of that is a carbon matrix composite. And we took that through several flight test profiles, up and down, up and down, up and down, and then a long duration profile that our vehicle will never see, but something like a hypersonic vehicle will. And it actually kept the interior structure cool enough that we would still be able to use our composite tank. And that was a huge, huge, huge validation of a concept for what we call a Duratherm, or durable extreme thermal insulation system. So we've completed that round of testing, and more testing on that front is coming up. So, and we've got a prototype flight vehicle that's going to take to the air this year. So that one, we haven't revealed a lot about that one, but that will get us in the air with our shape flying for the first time. So we'll have an idea of whether or not the controls for it operate the way we expect it to, whether or not it flies the way we expect it to, et cetera. Because right now you're doing everything in a computer, in a wind tunnel, and that's not the same.
I was going to ask about first flight, but what have you guys talked about publicly when you expect the first fully sized Radian spaceplane to be launching?
Yeah, the target for that, I'm going to look it up so I don't get any answers wrong here. See, I've got slides where I can see the domes and all this other good stuff over here. Okay, our first subscale flight, our first runway subscale flight will happen this year, and that's a jet powered system, so it's not rocket powered system. We're going to try and turn that into a sled takeoff in 2025, and then our first full scale system to orbit should take place in about 2028. Actually, 2028 is when it will fly, but it won't fly to orbit yet. So that's its flight test program, and the first one that makes it to orbit should fly, by 2029. So hopefully before the decade is out. Those are kind of the big milestone steps for us.
So we spent a lot of time talking about technology. I want to talk a little bit about more the business strategy, and specifically around the so talk for a second about the capabilities at the end of the decade of an of your orbital space plane, and then maybe contextualize that from the perspective of with all the existing and coming launch capacity, how are you positioning in the market? How are you positioning yourself in
Yeah.
the market?
One of the things I like to do is I like to differentiate what we do from other launchers, because other launchers are purely that. They launch stuff to orbit. Some of them have the capability to bring stuff back, but they typically take stuff to orbit. So the vast majority is a one-way delivery service. There's a smaller subset that is a two-way delivery service, but they always come back with just a capsule, and you have to, rebuild or reassemble your rocket back in the ground. And those are limited essentially by how big the capsule is and how big your parachutes are going to be, and whether or not you're going to land on land or you're going to land in the ocean. So those are are, are different than us, because we'll be able to take your cargo up and bring it back, and we don't have to leave it behind. And so there are things that you can do with just an open payload bay and look out. You could put a telescope in there for celestial observation. You can put a telescope in there for Earth observation. You can put sensors in, RF sensors to listen to the stars or listen to communications on Earth for both intelligence, surveillance, and reconnaissance, or space domain awareness. So these types of things you can try out. You can fly it. If it works, great. If you want to tune it to make it more sensitive to a particular, galactic spectra, you can do that, and you can refly your experiment. You don't have to build your payload and never see it again and hope that for its mission life it always works. You can still deploy that payload with us, but you can also bring it back if things don't go right, or if you want to upgrade some of the sensors on it, that kind of thing. So we end up with greater flexibility than what a traditional launcher will do, because we're a mission platform, and the platform has a variety of things it can do as a platform, as a deployer, as a retriever, et cetera. So that adds several new dimensions to the environment. And somebody else can launch something really big that we can't launch, but we can then go service it. So if you want to build a space station, you can launch a big module, that wouldn't fit in our payload bay, but we can bring up the crew to actually outfit that module, work on it, et cetera, and bring them home, and then take up the next crew. So rotating those crews is a little easier than it is today. So that's when you start looking at how does that fit into the build out of space infrastructure, that really kind of changes the thinking pattern. It's not just launching stuff, but it's actually building stuff in orbit and maintaining stuff in orbit and bringing stuff back. So, the flexibility really starts to increase as you start realizing that this is not purely a launcher. So
yeah, and I think if I have the numbers correct, I think what I saw was that your down mass capability was about twice, not exactly twice, but about twice the up mass
just about,
capability.
yeah,
Um,
yeah.
So one common use case that's getting a lot of I shouldn't say traction, just a lot of I've been hearing about, I should say. Well, especially in the
People are
context,
saying,
people are saying, especially in the context of Starship, is this
yeah,
hypersonic point-to-point
yeah,
travel, right? An Earth-based use
yes,
case,
yeah,
like for
yeah,
people and cargo. What do you think about
yes.
that?
Yeah, we are absolutely thinking about that. We are absolutely thinking about that. Matter of fact, the first vehicle that doesn't go to orbit, it may be a really good, point-to-point transportation system. So there's absolutely advantages of that, and so that's I think there's a there. We had, I'm recalling a conversation we had with somebody in the DoD whose function in life was to transport cargo, generally via airplane, and so that was their organization's reason for being. And they started thinking about what they have to do. And sometimes you're carrying troops and equipment, etc. Other times it's humanitarian aid. So you're carrying doctors and water and meals ready to eat and antibiotics, etc. And timeliness in in cases where you have a humanitarian need is really important. And so we said, what if we, and they said, and a lot of times they don't have good places for anything to land, not even C-130s, which can land almost anywhere. And so they struggle with how do I provide humanitarian relief in a really distressed area. And they said, if I could get water, antibiotics, and a sat phone to a group of folks that have been cut off from the world, that would be valuable. And he started doing some math on what it took to get X amount of water and meals ready to eat delivered to some spot on the earth using the methods we have today. And he concluded that maybe getting the first round of aid in minutes or hours rather than days would be vital to the survival of those folks um, in need. And and so he said, because we tend not to take just a little bit, we tend to take a lot. We have to stage what we do. If we go from the U.S. to, say, a location in Europe or in the Pacific, it takes that much time. You have to have tankers to refuel your cargo ships, et cetera. And so he started going through the math, and I didn't think about how many different stops and features have to be added to a flight to make that cargo delivery work. But since that was his existence, he thought about that a lot. So, and he said, perhaps we could overfly an area and drop that stuff down to people who need it. And we concluded that we could probably take something in the payload bay that was essentially a relief package and drop it within maybe a couple clicks of where the relief is needed quicker than almost anything else. And so you could have these relief packages built out for different scenarios and in storage ready to go should disaster befall us, like it often does around the world. So so those are different things that we didn't necessarily think about when we started, but they're enabled by us existing. So we don't always have to land. Yes, we can land in a 10,000 foot runway somewhere else in the world, but we can also drop stuff from orbit or near orbit to get to folks that need aid quickly. So interesting.
So it might be maybe it's a bit early to ask this question, but how does commercial and government traction look so far, or how have the
Good,
conversations been?
good, good. Commercially, we've had good investments to date, and it looks positive because I think people are realizing that we're different than other space systems and maybe a little more forward leaning. I don't know. And so that's a positive thing. The government keeps its eye on us because they start asking questions like, if you existed, could you do this mission? And we'll go off and say, we haven't thought about it. Let us think about it. And the answer more often than not comes back, yes. So I think that the government, the DoD predominantly, is starting to think about how could they use a Radian in their system. So I would characterize the responses that we've had as positive because it engages, it provides flexibility that they hadn't necessarily thought of because they thought of launchers and satellites, and and the two lived in different places. With us, a launcher is a mission platform, and it can do things that satellites can do, but it can also do things that you know cargo carriers can do, or retrieval missions. So it really starts to open up the aperture of how you think about space logistics, space operations, and it's going to take a while before the ideas settle in and say this is my first best use of this system. But I think that there are enough people thinking about it that I think it'll be very, very positive for us and a good point of entry for a lot of innovation in the future.
Any direct competitors?
Not really. We're kind of a little bit of a different animal. A lot of times people will compare us to anything with wings, like X-37 and Dream Chaser, but those are launched on a traditional rocket and have to fly home. So they're kind of a spacecraft with reentry capability, but they're not a launch capability. Um, uh, you look at Starship, and that's a huge mass carrier. It's a gargantuan mass carrier. So it'll get a lot of stuff up, and it can land too. But you really have to have enough mass or stuff to justify the launch of something that large. So we're a much smaller system, uh, and our payloads are smaller. So the analogy I use often is the construction of a building. When you construct a building, the big beams and things like that come in specialized trucks, and they're 18 wheelers and large cargo capacity, and they deliver them to the work site. And then you got panel trucks and other things that deliver sheetrock, glass, and some of the things that go in. And you'll also have pickup trucks for smaller things with work crews, etc. The work crews don't show up in an 18 wheeler. They don't show up in a specialized large carrier. They show up in smaller vehicles, like their pickup truck or an SUV, and do the work there and then go home. So is space transportation matures, the marketplace is going to spread out. You'll have more customization for different sections of the marketplace, and those systems will have value for the features that they have. For us, it's reusability. You take something up, you can bring stuff back. You can take people up, you can bring people back. You can stay on orbit as a mission platform and do stuff while you're there, and then come home and tweak your mission payload. So I think that level of flexibility is really going to change the thinking, if you will, of the marketplace. And I think it just broadens the spectrum of, if I want to do this, then this vehicle's a choice for me, or that vehicle's a choice for me. But it just really broadens that spectrum of thinking.
Is this something that's going to cost like $1 billion to build?
It's expensive.
What any upcoming?
Yeah, I'm not going to release any numbers to build it, but it's like anything that's really new and different. I can't go find a ready-made capability to go do that. So I have to build a lot of those features and characteristics myself. But what we're really trying to do is leverage what's been done. For example, the materials that we're using for our composite tanks, the basis of that material all exists. We're just applying it in a different way. The materials that we're using for our thermal protection insulation systems, the basis for those materials already exists. So that's why we're able to actually put together a full stack and test it very quickly. Some of the work had to be customized, such as the polymeric aerogel that NASA Glenn built, but they almost had building blocks, chemistry building blocks. They said, if you want these characteristics, I will apply these chemicals in this manner and develop it like this in order to get you what you need in terms of your capability. So a lot of the building blocks exist, but we're just using them differently. And so, so that's going to end up, creating some additional demand for development testing that you might not have on a simpler cylindrical aluminum rocket, things
Right.
like that.
Any upcoming fundraising plans that you'd want to share?
There are upcoming fundraising plans.
Okay, we can leave it at that.
I'm sorry.
Hey, some people just say no, or some people just don't even want to answer. So I appreciate it. It was a solid answer.
This is a non-trivial problem, and it requires capital to keep going. And so we'll continue to raise capital as we move forward. That's probably a better official answer.
Yeah,
How's that?
absolutely. All right. So my last, final, hardest question, Livingston,
Okay.
which is, what do you do for fun?
Oh God. Well, see, first of all, I just went to you're going to find out something personal about it. I just went to my 45th Air Force Academy reunion.
Oh, wow.
45 years since I graduated from that school. All my classmates are out of uniform, and they're sitting on a lounge chair, uh, you know, leaning back, drinking lemonade, and they're going, "Why are you still working?" That's not true of all of them, but there's a lot of folks that are retired. And I said, "I'm having fun. I enjoy this. I really do." There are young people that are just amazingly smart that have joined our team, and I get exposed to them. Like the cadets at the Air Force Academy, they're all seniors. One of them wasn't just a pilot, but he was an instructor pilot. So think about this: you're a senior in college, and you've got enough flight time and experience that you're teaching other people how to fly. Okay, it's not a standard thing, right?
Yep.
And so when they did the wind tunnel test, by the way, they got a grade for this. They actually were graded because they built it into the course curriculum on how well they analyzed our performance in the wind tunnel. And I'm looking at this and I'm going like, these guys are brilliant. I mean, I tell you, that's pure joy working with young people that are way smarter than you were at their age, and you can see the wheels turning. That's energizing. That's absolutely energizing. So I love doing this work. And the other thing that I actually enjoy is I like being out in my yard. I go out and I'll trim back blackberry bushes and try and keep it from taking over the yard. And the dog and the deer and I will be out there with the bobcat and the bear every once in a while. And but I just enjoy being out in the yard and doing that stuff.
I appreciate that. There are mundane, and sorry if I call what you're describing mundane, but there are certain tasks that as a younger person, I would have said there's no way I could derive any value or fun from that. But there's just certain things now that I'm just like, this is fun. This is nice. This is relaxing.
When the weather's good enough and I can get on the lawn tractor, it's like cutting the grass has now turned into something that's fun.
So as an engineer, are you someone who you go into a Home Depot or whatever and you're like always looking for the next, the best, the biggest,
yeah, there I remember I talked about Jeff Feige earlier. He was over to the house years and years ago, and I had a plumbing problem in the basement. Yes, I designed the house. I designed the water system in the house, so it actually acts as a fire suppression capability, but also all the potable water comes from the well, and so I've got multiple pumps, et cetera. So it's a complicated thing. So I needed an overflow valve because I had a flood, and I was doing the tubing. And I said, "Oh man, I got to get down to Lowe's before it closes." And we went tearing down the mountain. We live on the mountain in this kind of a winding, not very smooth road, and Jeff's in the car holding on for dear life, and we get to the store and I talk to a guy and he said, "Oh yeah, I got what you need." And he goes, "Why does it seem like everybody in this store knows you?" I spent a bit of time here, so yeah, so it's there's a little of that.
Yeah,
but I enjoy that. I enjoy the tinkering that I do, in the yard, around the house, in the house, etc. And so that stuff is, I'm easily entertained. Let's put it that way.
I love it. Well, Livingston, thank you for entertaining us for the last hour. I really appreciate it. It was a great conversation and super interesting one. And look forward to staying in touch and on top of all the progress that you guys make.
Thank you. And I look forward to our next conversation. With each conversation, we can reveal a little bit more, and I think that's exciting.
Perfect. Until next time, Livingston. Thank you.
Okay, we'll see you. Thanks, Bob.